All right, everyone. Thanks again for attending. Hopefully you had a nice long weekend. We're going to kick it off with 5-6. And the root word to what the title of this chapter, section 5-6 is ratio. And so what we're going to be talking about are other types of functions to add on to all the others that we've been speaking about in depth. And that is a ratio or rational function. For lack of a better term, a ratio is a fraction. Okay, but of course they're going to be functions, which means we're now going to have what are called numerators and denominators full of x's and coefficients. Okay, so the top numerator and the bottom denominator could look anything like that. And as we've been studying so far, we know that the denominators cannot equal 0. And we'll talk about what implications that has when we're also digging in deep into the graphs of these things. But to start it off, that tells us what we can and cannot input. Remember, inputs were the x's, the domain we called it for technical terms, all right? And the domain was all of the numbers that we could put in, real numbers, positive, negative, whole numbers, or fractions. But the domain, what we're going to find are the things that actually cannot be put in, that when we work it out in the top and the bottom, we don't get a y value out, no output, no range. And that will only occur when the denominator is equal to 0. Okay, so we're going to say it's all real numbers except the things that give us a 0 in the denominator, which they're calling q of x, because it's a function of x. All right, so nothing really new there. It's just going to be the look of it. Okay, and so the first thing we're going to talk about is if we're given these new things, quote unquote, called rational functions, and we want to find the domain, we're not even going to focus on the top. We're only going to focus on the denominator and setting it equal to 0. Now, hopefully, like we saw in some of the things we were dealing with last week, maybe they'll already be factored for us. Sometimes towards the end of that group quiz, numbers 10, 11, 12 in that range, they weren't. And some of you guys either left them blank, had no idea where to start, or just kind of worked backwards and said, oh, here's the answer key, so I know that these have to be my factors, and you didn't show me how you got there. Okay, so unfortunately that's not going to work on the test. You're going to have to show me. All right, and so we have to make sure that we know how to find these things. All right, so if you don't, ask questions. Me, group quiz, whatever works, discussion board. All right, so we've already talked about this before, we've already done this before, but now we're going to get into more detail. Okay, so we want to know what are the characteristics of all rational functions. Well, remember the key word there is ratio, and a ratio is a fraction, and therefore all rational functions, their graphs have what are called a numerator and denominator, those functions and their graphs that we're going to be dealing with here in a minute. Okay, so what does that result in? We will have asymptotes involved. Okay, and I'm just going to leave it generic like that. Part 2 of the characteristics, we want to talk about what we can put in, and then we'll just kind of figure out what we can get out of that. Okay, but the domain is the key, the inputs, or x values. And remember, since we're dealing with numerators and denominators that are polynomials in nature, then the domain is dependent on its what? Denominator. And the denominator we will set equal. We know it cannot be 0. Right? Now, one other thing I want to mention, because quite a few of you are doing it for whatever reason, I don't know why. What does this mean in math? That
Not equal to 0?
No solution?
anybody else?
No answer.
And do you see what we're getting? Are a bunch of different answers. Go ahead, Mel.
I just write my zeros like that.
And that's a
All
problem.
of
and
them.
that's what I'm coming to let you guys know is I've seen this from quite a few of you, and not just in this class, but in my others as well. That does not mean 0. Okay, we already have a symbol for 0. It's this. Okay, if you write that, that means theta, which usually represents an angle. It's a Greek letter.
Oh.
If you write this, that means no solution or empty set. Okay, so I know it was cool to be different back in junior high and things when you probably started writing your zeros like this, right? But please stop, because you may have teachers that are going to get a little stringent and be like, no, that's not. There's an answer. It's 0. It's not no solutions. There's a solution and it's 0. Okay. So again, just be careful with that, because some of you guys are writing it like that, and I've been writing it on there, but I don't know if you guys are even looking back at them. So I wanted to mention it while I hopefully have all of your attention. Okay. So just put zeros, plain and simple, as the symbol that was created a long time ago. All right. Now, do some of these graphs look familiar? Do you remember the 1 over x we called the reciprocal function? Because it's if we have x, y equals x. Well, if we did the reciprocal of that, flipped it, then we now have an issue. And just one, because this is to the first power. And remember, the degree told us how many possible zeros there are. So for this one, how many possible zeros are there?
2.
There's 2, but they both happen to be the same. They both happen to be 0. But if we had x squared plus 3x minus 4, now when we set that equal to 0, we will have 2 different ones. Okay, so these are the most basic. Remember, we call these the parent functions of some of these. And if you notice, we have a vertical asymptote. And remember, those asymptotes were where our graphs approached, but never actually touched or reached. And those vertical asymptotes would happen at these, what are called lines. And that would be where x is equal to something or y is equal to something everywhere. What's true about up and down this line? Are all the x's or all the y's the same?
X is equal to 0.
Very good. X is equal to 0 everywhere. We're not right or left anything, but notice my y's can be anything. So we're not going to even list it. Okay, that goes same for this. Or any other vertical asymptote, it would just be at different values, like x equals -3 or x equals +2. And again, those will depend on the denominator in our domain. But we're going to add in another thing today called a horizontal asymptote, which we've kind of spoken about a little bit previously. Okay. If you can see, I also have a horizontal asymptote. But this time it would be at what?
Y equals 0.
So does it matter whether you put x or y? Absolutely. Okay. So with that, we are now going to be seeing that, yeah, it looks like these are getting closer and closer to what?
0.
Very good. Which means, remember the end behavior stuff we talked about? Now, again, careful. Some of you guys are writing it the way that the answer key has it, because I'm kind of restrictive on how I can write these, or the program I use only says it this way or that way. How would I want you to say this? As x approaches, and that's the symbol we use for approaches, just an arrow. It goes to -infinity. What does my f of x, or I'd be fine with you putting y, approach? And again, as x approaches, let's go to the far right side. And if you don't put the positive, it's implied. So again, that matters. what is my y approach? Remember, a lot of times the end behavior was it shot up or down indefinitely, which meant we put infinities. But this time, what am I approaching to the far right and to the far left?
0.
Yeah, now we're going to actually have that number 0. Okay, not the letter O, not no solution, not theta, but 0. Okay, so you got to be careful. This is familiar, I hope. But when we approach a number now for our y values, that is going to imply that we have in the extreme left or the extreme right, when it approaches some number, we're going to have what is called, it's pretty funny, a horizontal asymptote. All right, so be careful. A lot of familiarity here, hopefully, but something new in that we are dealing with these things called what?
Asymptotes.
Good. Horizontal asymptotes, to be specific, Jenny. And what kind of functions?
I want to say reciprocal functions, but I don't think that's right.
Good. Those were only those. We're now dealing with rational functions in general. These are just the most basic ones that we can deal with. So that's why I'm starting with those. Okay. Of course, ours can look way uglier. Okay. So hopefully you guys see why we've been dealing with in the previous week, those previous 3 sections, how to set things equal to 0 and solve for those solutions, those roots, those zeros, we call them, or X-intercepts. Because now when we set that bottom nasty old polynomial function equal to 0, that's going to tell us what things we cannot have in our domain. So again, we can put all double-legged R stands for real numbers, except X cannot equal this, this, or that. Or we can put from negative infinity to something, including that, union, blah, blah, whatever. Okay, or excluding whatever we want to put. So to summarize here, we're going to talk about this. They call it arrow notation. What does that arrow mean? What one word?
Approaches.
Very good. Now, something that looks a little weird. Notice what this. A standing for anything, any number. You know what infinities are. Positive to the right or up, depending if we're looking at the X or the Y. Negative, left or down, depending on the X or the Y. But what about approaching a number? Well, this is obvious. That's something that we've already done and seen, and I just reviewed with you. But this, not so much. And you guys were first introduced to positives and negatives on what were called the number line. And remember, what was the one thing that we measured, separated the positives and negatives with?
Distance
From what?
from 0.
Good. And that distance, we either had to go to the right of 0 or to the left of 0. And to describe which direction we wanted to go without saying words, we like that in math are symbols. And we made this up to the right, this to the left of 0. But of course, are we always going to be right at 0? Of course not. We can be at any number. So what these negatives and positives following a number are going to mean is to the what and what of that number. Just like our number line. If we're at 0, to the right was positive, to the left was negative. But notice they put it after the number. Because if I put -5, what does that mean to you? If you're starting at 0?
It would be 5 to the left,
That's right. And if I put +5, you know to go
to the right.
exactly. So this is something that you're going to learn in the first semester of calculus. Okay? When we're talking about limits, this is the symbol they use with limits. Because remember, a limit is what you're approaching, not what you are at. Okay? If I wanted you to find a value, I would tell you pick anything, plug it into your function, and tell me what you get out. But for limits, for this class, we're going to be talking about this arrow and what it's approaching. Now notice, what is the one commonality that all of these have? Besides the arrow.
X is
Very
approaching.
good. So if they're telling us the X, guess what they're going to want us to give them?
The Y.
Very good. And if these are telling us what the Y is approaching, then they're probably going to want to know the X value. Okay, so pay very close attention to those things and make sure that you understand this negative or positive after following some number. That means from the left if it's negative, or from the right of that number. Because if I go back up to this graph and I want you to tell me what my Y is approaching, if or as X approaches 0 from the right. Or from the left. Who can tell me what the answers would be for this one here? And think about it just for a second. Let everybody think, Brian. I saw you chiming in. I appreciate it. Let everybody think real quick. All right, what do you think? Again, what are they asking us for? And what did they give us? And what does that symbol mean? And what does that symbol mean? As X approaches 0 from the what?
The right.
So from the right, as my X goes closer and closer to 0, what does my Y value approach?
Infinity?
Very good. Positive, negative?
Positive.
Positive.
That matters. Very good. And this one says, as X approaches 0 from the left. So as my X comes closer and closer to 0, this time, what does my graph do?
Negative infinity.
And again, that's why you guys need to put arrows on the ends of these things. Very good. Excellent. Now let me just throw one more thing at you here. As f of x approaches 0, what does x approach?
Positive infinity.
Is that your final answer?
Maybe. I don't know. Feeling shaky now.
Yeah, this is new. It's all right. This is saying now, what is my y approaching? Well, 0. So we're looking at the y value now, either from this side or this side, approaching 0. And where does our graph approach 0? Well, when the x is, somebody said positive infinity, but where else does it?
Negative infinity.
Very good. So you could put plus or minus, or you could write a whole nother thing as it approaches 0, not equals 0, but approaches, or x approaches negative infinity or positive infinity, or put them both. Excellent. Very good. So again, got to be very careful in understanding what this is saying. Depending on what they give us. Okay. All right. So we talked about the vertical asymptotes. That's going to be at some number. Our y is going to either approach positive or negative infinity. Why do vertical asymptotes always approach positive or negative infinity? They're vertical. That means they go up and down, right? And if they're going up and down, that means our y is going to approach positive or negative infinity from either the right, the left of some number, or both sides of some number. It just depends on the graph. But notice it's approaching either positive infinity or negative infinity from one side or the other, or even both sometimes. Okay. So what are we trying to do here? If we're given a nasty old rational function, we want to identify the vertical asymptotes. And how are we going to do that? The same way we find the domain. So I'll leave this here in case anybody wants to write this down. Let's start with an example for finding the domain, and then we'll do an example to find the asymptotes. Because guess what? The process is the same. So you really got to know what they're asking you to find. And if I want you to find the domain, how do we do that when our function is a fraction? We call a rational function. How do you find the domain?
Denominator equal to 0.
Good. And that's going to tell us what though, Brian?
Where x's are,
Or what?
or domain.
What about the domain? Getting warmer, but I want to make sure that you understand this, everyone.
Is it where the asymptotes are? Is that what we're after?
That's true too.
Okay.
But they didn't say anything about that yet, right? For this example, all they want you to do is find the domain. And remember, the domain is all the what?
All the inputs, all the x's.
All
Are
right,
you
I see it now.
seriously going to sit here and test every single x value? You can't. You die trying. Because there's an infinite amount of numbers. There's an infinite amount of numbers between 0 and 1, let alone to infinity and negative infinity. So, no, we can't. What we're looking for, Brian, is all the things that what?
It can't be.
Very good, Peter. That can't work. And
I
so
was so
technically,
close.
yes, you were. I was trying to get you there. Technically, it should be this. Right? These are what our x's cannot be. Because obviously, you'd factor that or add the 9 over, take the square root, and you'd get two answers that x cannot be. X cannot be negative and positive 3, which means everything else. Or if you wanted to write that in interval notation, from negative infinity to negative 3, not including it. And then from negative 3 to 3, not including either of those. And then from 3 to positive infinity. I'd rather not write all of this when I can just say everything but these. And for me, I don't care which. Okay, your homework may request one way or another, so just make sure you write it. But either way for me is fine on the group quizzes or your exam. Okay? So remember, when dealing with these, Brian, where you were getting a little confused, and it happens, but I want to try to alleviate that. What else could we have done to start graphing this function? Well, we would have started what things we can't have. Now, one thing I want you guys to notice about this problem that's a little weird is if I took it and I took the x plus 3 and I factored the x plus 3 over x minus 3 on bottom. There's my function, right? What does it look like I can do right then and there?
Cancel out.
X plus 3.
And if I do, then I get a simplified version of what they originally gave us. Is technically this the same as that? Yeah, but remember, I told you guys one of the most important things in all of mathematics is multiplying by that special 1. Because when we multiply by 1,
We just get that back.
and notice that's why we can cancel things, is because it's just a 1. And we know 1 times that is still going to be that. But remember, guys, this is what they gave us, not that. Because if you give me the simplified form, you would only have 1 issue and not the 2 that you should have had. So what does that do graphically to us? Nice little segue here. When you can take things and cancel, we get what is called a removable discontinuity. What the heck is that? That's a mouthful, right? Better yet, it's known as a hole. It's still a discontinuity, meaning that there's gonna be some asymptote, some part where I have to pick up my pen or pencil and then do it again. It's not continuous, discontinuous. Or when we have that situation where it cancels out from the top and the bottom, some common factor, what ends up happening is no longer a vertical asymptote. If I was to graph this, I would not have a vertical asymptote at x equals -3 and x equals 3. But there would be something happening weird there. I would have that discontinuity where I'd have to pick up my pen or pencil. And it is what is called a hole. There would be no y value. Because do me a favor, everyone, go back here to my original function and find what f of -3 is. What do you get on top?
0.
0.
-3 plus 3, very good, 0. -3 squared is 9 minus, and now we just have a division symbol like we used to draw in 4th grade of elementary. We don't know what 0 divided by, we cannot divide by a 0. And of course, if we plugged in a +3 there, there, and there, we would have a 0 and then a 6. And we can't take 6 and divide by 0 either. Which is why we have those vertical asymptotes. But because we could rewrite this, that removable discontinuity, they call it, would give us a hole in our graph. There'd be one point, one value where we'd have just an open dot. And if you guys want to know where exactly that open dot is, don't you already know where the X is? Where would that hole be at?
-3.
Good, but that's not a point. Get my
0.
point? Would it just be 0? I don't have to be up or down any? Well, check it out. Once you remove it, you can actually now plug in that issue that we removed for X. And if you do, that means you just got out the Y value.
Okay.
Do you see it? So
Yep.
if I was to plug this in to this simplified form, I would get a Y value out. So what would that mean I would get?
-1/6.
Good. 1. And if I put in a -3 there and subtract 3, I get -6. So I actually know exactly the location of that hole or open dot. Cool? So that's what a removable discontinuity is. And we are going to move on to the last thing of this, and we'll tie it all together, called a horizontal asymptote, which I already gave you the preview of earlier. Okay. Horizontal meaning now we're going to have some y value. It's up here, it's down here, it's 0, whatever. The x's can be whatever now. Okay, but y will always be some number. And so they use x equals anything, and then therefore to make sure that you know it can be different, they use y equals anything else. So a b, next letter in the alphabet. Okay, so again, whether it's approaching from the right or from the left, for our x values, we are going to approach some y value called b. So let's say it's 3. That means way out here and way out here. I could be approaching, say, from down here or up here, or I could be approaching from up here or down here. It just depends on the function. I can't have all of those because now it's not a function. It doesn't pass that vertical line test that we talked about. Okay, so it's one or the other. This one or that one. This one or that one. So how do we tell? We'd have to plug in some values. Right? So how do we find these things? Here is a nice little hint that I'm going to give you guys. A shortcut, if you will, to finding horizontal asymptotes. These funny things that are a little bit more difficult to find. Vertical asymptotes, easy. Set the denominator equal to 0. Done. Those will give us where the x's are for our y's going up and down, those dashed lines. Okay? But there are 3 different scenarios with these. And I will highlight all of them for you. What we're really going to focus on is the degree of each and every one of these things. Now remember, this is what they look like in general. And remember, the degree is the highest exponent of these things. All the rest of this, then, we can pretty much forget about. We're just going to focus on the highest and the lowest degree. Because what did they say horizontal asymptotes are? The extreme right and the extreme left. And can you actually physically go to your function and plug in infinity or negative infinity?
Nope.
Maybe. I agree with your answer though, Brian. No, because infinity is just an idea. I can give you a really big number and then you can add 1 or 100 or 1,000 or 1,000,000 or a Googleplex. Yeah, really big numbers, but no, it's kind of silly to even think about it. So all we're going to do is focus on those exponents. Because what we can do is actually take any ugly rational function that they give us, and we can always multiply by what, my friends?
One.
Very good, Jenny. A fancy 1. And what do we always have to worry about with these rational functions? The denominators. We cannot have those be 0. So whatever we divided by, we'd have to be careful and make sure that we didn't get a 0 in the denominator. So I'm just going to focus on the highest exponent. I'll show you this on part A, and then hopefully I can just verbally explain the rest so we don't have to do this again. And the better you understand this, the easier calculus when you get to this will be. I'm going to take this, which I know is what they're calling g of x, and I'm going to multiply it by a fancy 1. Now I'm going to get super fancy. Y'all ready for this? I'm going to look at the x cubed. I don't care about the 2, just the unknown variable. And I'm going to divide everything by an x cubed. Now, can I do that?
Yes.
I can do whatever I want. as long as I do it equally if it's an equation or something that doesn't change it. And this is a really fancy one. So I'm going to divide this and that in the numerator and this and that in the denominator by x cubed. And watch what happens, everyone. Ready? What's going to happen when I divide this by x cubed?
Doesn't it get rid
Of what?
of the x cubed? 6.
Good. So I'm just left with the 6. Right? And it's really small, so otherwise I would write it under there. But dividing this by x cubed, dividing this by x cubed, I just get the x cubes cancel to get a 6. And then I would have plus, that was a plus, right? Or a minus?
Minus.
Thank you. Minus one of these with one of those. So now I'd have 10 over x squared. Looks better already, doesn't it? Yuck. But there's a reason to this, okay? Just watch. Bottom, divide that by x cubed and that by x cubed. This one, the x cubes also cancel, so I get a 2, and then plus 2 of these with 2 of those, so I'm just left with 5 over x. Now, does everybody agree that my original g of x function, this is the same? How do you know that is true? Even though they don't look it? All I did was multiply by a what?
Fancy one.
And when we multiply by 1, we get the same thing out. But why am I doing this? Well, remember, we were trying to see when our x approaches infinity or negative infinity, what did our y or f of x or g of x approach? And we said, Brian, we can't plug in infinities. But what happens if I plug in an infinity there and square it? What's a really, really, really big number, you know, squared? It's even bigger. And what happens when we take a 10 and divide it by a really, 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 you get my idea, big number. What does it approach?
0.
Very good. Excellent. So this is just going to go to 0. Which means, what is this going to do when we plug in that infinity, that really, really big number for x? It's also going to go to 0. And notice, what are the only things that are actually left?
Six over 2.
Which means, what do we just find that our y, our output, would give us when we plugged in infinity for x and made those disappear?
Approximately around 3.
I like how you said that, Ellen, approximately. That's what this is saying. Is it exactly 3? I don't know, because I don't know what infinity is, but I know it's approaching that number. Now, guys, what would happen if we plugged in a negative infinity? Is that going to change anything? Or would these things still go to 0? What happens when you plug in a negative really big number and square it?
Positive.
Becomes
Positive and then even bigger, right? So this one's all good. What about here? A negative really big number. What's 5 over that?
once you just get to -0, which is just 0.
Very good. What does the negative represent?
On the left side.
Boom. Very good, Jenny. Excellent. It's from the left side, positives from the right side of 0. It's still approaching 0, just from the other side. Very good. So that means I don't ever want to do that again. If you want to see it again, rewind this and watch it again. Okay? Because I want a shortcut. I don't want to have to multiply by this fancy one and do all the dividing and simplifying and then get that and then think about what it would approach when I plug in positive and negative infinities. I want to get there quicker. So check it out. Let me erase this. Now I want you guys to look at this and forget about all the other little parts, because when we're plugging in something really big, we're only going to focus on the biggest things on the top and the bottom and see who wins that war. And who's going to win this war? Well, usually it's whoever has more people. Not so much anymore. Now it's all about intelligence, right? But we're going to think of it as whoever wins has the most. And if you notice, on top and bottom, it's a tie. The biggest on top is an x cubed. The biggest on bottom is an x cubed. So guess what's going to happen? They're going to cancel out like we just did, and you're only going to be left with the coefficients. And look, it tells you what your y is equal to. Here's my y. Here's my value that we're approaching. Done. But of course, what happens when they're not the same? Well, let's think about that. Let's think about all that stuff that I just did. If I looked at these two, who's going to win? The top or the bottom?
Top.
And if the top wins, then we know the bottom is just going to kind of cancel out, and it's either going to approach positive or negative infinity. And if the bottom wins, then what do we know that's going to approach? It's going to also approach that positive or negative infinity, but on bottom now. And we said what happens when you have a number divided by a really, really big number? It approaches what? It gets close to what?
0.
Excellent. There's your shortcuts. And as long as you guys just circle this and kind of let me know that you know the shortcuts, I'm all good with that. You don't have to do the whole multiplying by 1. I just wanted to show you that once so that you guys understand why these shortcuts work. Okay. And again, here they are just in case. All right. If the numerator is less than the denominator, then it's going to approach 0. If the numerator is greater than the denominator, then we will have what is called a slant asymptote. Now we know asymptotes to be vertical, straight up and down, horizontal, left and right, but every once in a while you'll have one that's slanted. What are all of these? Don't make me keep dancing.
Angles?
Close, Alan? Graphically, let me clarify. Graphically, what is that? What is that asymptote? And what would this asymptote be? Go ahead, Mel.
Straight line.
They're lines. And if they're lines, then what do we need? We need equations for those lines. And we know if it's going up and down that vertical asymptote, then it's what? If it's up and down, y can be anything. So therefore, it's going to be x equals some number. And again, we're going to put, instead of the number sign, we'll put a to represent anything. If it's a horizontal asymptote, now my x can be whatever. But then the y has to be something. So y equals some number. And if it's slanted, then what is true about that line, whether it's negative or positive? What's negative or positive? It's still a what?
Slope?
Very good. Very good. It's still a line, but now it has either positive slope or negative slope, which means we're going to put it into our slope intercept form. Now, how are we going to get there? I'm all good with this being the whole 0 thing. I'm all good with, let me finish it off here. all of those options, I prefer this one. I really like this one. This is my least favorite. So I hope that the numerator is not greater than the denominator most of the time. I prefer them to be equal because then I can just take the 6/2 and there's my answers. But if it is bigger, then guess what we're going to have to do with this? We're going to have to rewrite it. How are we going to rewrite that? We're going to do what it says. And what does this right here mean, my friends?
Divide.
Dang it. That means we're going to have to divide. The good thing is we learned 2 different ways last week to do that. What are those called?
Long and synthetic division.
Very good. Which do we prefer?
Synthetic.
Maybe you, Jenny. Don't speak for everyone.
I like it too.
Yeah, most people do. She's absolutely right. But if you don't know how to do it, then obviously you're going to have to use long division because you should know that from 3rd, 4th grade and on. Okay. But be careful. The only time you can use synthetic division is when it's linear and it's x plus or x minus something. Otherwise, yes, you are going to have to use long division for others. Okay. So just to remind you, if I was to do this one here, I would rewrite it as a -2. And then I got my 2, 1, 0 power, so I'm all good. I would have my 1, -4, and 1. Bring the first one down, literally, it happens to be that. There's our setup. We go to work. Multiply, add, multiply, add. And remember, because it was x squared over an x, we're now going to have an x to the first and then no x's there. So this would be equivalent to x squared minus, excuse me, not x squared, x minus 6. Now, what about the remainder? Do I want to put x minus 6 plus whatever the remainder is over what we divided by? Definitely don't want to go the pirate route like a lot of you were and put the R. That's like so 4th grade. Okay, we're not gonna, we don't still believe in pirates, do we? So with that, remember what we're actually approaching is infinity. If we plugged in an infinity there, this would just go to 0 anyway. So we're just gonna stick with that. And this, my friends, would be what is called my slant asymptote. Again, I did not change what I had. I just changed the look of it. Okay. So that's pretty much it in a nutshell. Did anybody still need any of that? Anybody still ready? Okay. So can we put all of that together to finally do what we're set out to do? And that is sketch a graph. Now, when they say sketch, that's really nice for us because what does that mean they don't care about?
Accuracy.
Yeah, all the little details. Now, some of you guys on the last group quiz were like, whoa, bro, I can't graph -2300. Okay. And I didn't expect you to, but that was really cool that some of you guys actually found the y-intercept. Okay. But again, they give you an 8-step process to find it. You guys know what to do. Find everything you can. Okay. That goes for intercepts. Easiest one we usually said was y because our functions are telling us what y is equal to. Just let the x's be 0. Okay. Then it says to factor the numerator and denominator if it's not already, which hopefully it is. Okay. And then remember, we're going to focus on the denominator and we're going to see where those things are equal to 0. All right. Multiplicities, all those things tell us some of the things that we talked about before, whether it hits and bounces back even or goes through. And remember, the higher the power, the more it will flatten out about it and continue up. Okay. So if I was to give you this example right here, would you be able to do all of that Hopefully. We just talked about it. Okay, do you guys want to go over this one or do you want to just try it on your own? And we'll move on. It's up to you.
Yeah, I would like to go over it.
Sure, okay. So this one says to find all of the intercepts, the x-axis or horizontal, the vertical y-axis or y-intercepts, vertical and horizontal, or if there happens to be a slant asymptote, and then use it all to sketch. So what are we going to do with this function? Where should we start?
The horizontal intercepts.
It doesn't matter. That's the cool thing. Yeah, we could definitely start with that. I like that because if I let this and this be 0 and that be 0, all of that 0 stuff wipes out, where this, it would be a little bit more work because it's factored. And then I'd have to put the 0 here, 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 and here, and then take the numbers and multiply them all and then divide them. This is way easier because that, and that wipe out, we get what?
3/2.
When 0 for x, we get -6/4, which would be 3/2. That would be what is called our x-intercept. Very good. Could we find our y-intercept? Sorry, that is my y-intercept. Excuse me. How do we find our x-intercepts?
Set the numerator to 0.
Very good. Why just the numerator?
Because if you worked it out from the beginning, it would end up being x² - 4 over 0, which would equal 0 anyway.
Because that's what would make my y equal to 0. Very good, Mel. So I'm going to go ahead and factor this before I do any of the other parts. Okay, but this is a good place to start. I'm going to factor x minus 3x plus 2 would multiply to -6 and combine to a -1. Okay, make sure you know how to factor by now. If not, it's going to be real tough for you in calc. Okay, difference of two squares, x plus 2x minus 2, to multiply to -4 and combine to 0 x's in the middle. And now, like Mel said, it's going to be real easy to set the top equal to 0 to get my y-intercepts. They're going to be at what? Sorry, I keep misspeaking. X-intercepts.
3 and -2.
So 3 would make my y 0, and so would -2. And then I also know if I set the bottom equal to 0, that cannot happen. That gives me what?
It's got the whole.
Ah, good. You didn't even let me get there. You already started seeing it. Very good. If I set the bottom equal to 0, remember that's what we said would not be in our domain. Those were either vertical asymptotes or that special circumstance that happens every once in a while. Of course, I wanted to hit it one more time with you with this example. When one of our issues in the denominator can be removed, simplified, canceled out. So we're not going to have a vertical asymptote at that value because of that, because we can cancel that out, but all of this stuff will still be in play. Okay, so my vertical asymptote, I will only have one of them, and it will be where x is equal to 2. Y can be whatever. So I know over at my graph right now, I can go over 1, 2 tick marks. And remember, it's a dashed line because that's not part of my graph. Then from here, we also said that we will have a hole. And we know the x value would be at what?
-2.
Very good. That was the -2 because of this. And what did we say we would do to find the y value? If we ever want to find the y, we need to know the x to plug it in and get it out. Problem is, it doesn't work in the original. But once we got rid of that and we got rid of that, now we can plug in the -2 here and here for x. And that would give me -2 minus 3, which is -5, over a -2 minus 2, which is a -4. So 5/4. So if I wanted to graph that, -2 up 1¼ right there. Now at that point, what should I actually be putting?
Circle.
Very good. A hole. I have a hole in my graph because at my original function, if I plugged in that -2, I would have a 0 here and there on top and bottom, which means I'm not going to get a y value out, but I will approach this from either side. My graph will. Now this vertical asymptote, I know one of two things. It's either going to approach from the right or the left positive infinity, or from the right or the left negative infinity. But what the heck else does the rest of the graph look like? Well, there's one other thing that we could find, and that is our horizontal or slant asymptote. And for this one, what are we going to have? Horizontal or slant?
Horizontal.
How come? Forget
Equal.
about everything. Just focus on the top and the bottom. And what will it be, Brian?
1/1.
Very good. So we just found what's 1/1,
Where a horizontal asymptote is.
which means what? It's a
Y
line. And go ahead, Mel.
Y equals 1.
How do you know it's y equals? Look, it literally shows you y is equal to 1. Boom. Where is y equal to 1? Right there. Now remember, this is for the extremes. I even usually don't even put it in here. I only put it out here and out here. It will never cross a vertical asymptote, but your graph sometimes will cross through a horizontal. The horizontal, remember, asymptotes are only for the extremes, where our x is approaching positive or negative infinity. That means only out here or out here, not in here. Okay, so be careful with that. Don't let it throw you. So what else can we do to graph this? Well, I'm going to draw a quick little number line, and I'm going to test some points, because I know that these were my issues, my domain, and those were at -2 and +2. So I know that it's cut into basically 3 different sections. And remember, since these are x's, we're looking for our y values. And we want to know, are our y values positive or negative? And based on this, we can test here to see whether they're positive or negative by just choosing something way out here, in between here, or way out here. And that will tell us whether we're above or below our x-axis for our y's. Okay, what I usually like to do is I like to start out here in the positive. And what number do most people pick?
One.
Now careful, 1 would be in here, right? I like to pick something out here to the right. And what is the next tick mark in line?
3.
Most people pick 3. I don't like picking 3. I want to get a little bit more extreme. I want to pick something like +100, because all I'm caring about is whether my y value is positive or negative. So go back up to my original function and plug in +100. and tell me whether it comes out positive or negative. Well, I already know that it factors to be these things. And why did I choose 100 over 3?
Easier to figure out.
Doesn't 3 give me a problem, by the way?
No.
What if I plugged in 3? Is it positive or negative there?
+3 or -3 if you plug it in?
Positive 3.
Wouldn't that be? So if you plug it in, that would be 0. Because if you plug it in at 3, it would be 3 minus 3, and that gets you 0.
Very good. That's a
It'd be
problem.
0 over 1, which would
That's a problem, guys. You can't just focus on the bottom anymore. You have to find the zeros on top and bottom and use those on the whole thing. Does that make sense?
Yeah.
Because, let me use the same color here. These represented are X-intercepts. Not just where things don't work. We need to know where it crosses through as well. So unfortunately, that's why we have to test every 0. So that's a good thing. You don't have to think. Use all zeros on top and bottom. So I chose the -2, the 2, and the 3. And I know it's either going to be above or below in each and every one of these. Okay? Positive or negative in every interval. And do you guys remember all the multiplicity stuff we talked about? That will allow us to do a shortcut on this. So check it out. Couldn't use 3. Wanted to show you that. I'm going to choose my 100 that I was mentioning. And when I plug that in, all I want to see is if it comes out positive or negative. So I don't even care what the value comes out. Okay. Plug in 100. What are you going to get here?
97.
I don't care. What is it? Positive or negative?
Positive.
Good. What here?
Positive.
What here?
Positive. And
What here?
positive.
See why I didn't choose like 4? It's just easy to pick like 100 or 1,000. So just pick something easy where you can see that all of these are going to be positive. So this whole interval is going to be positive. Everything to the right of 3, which is right there, is going to be above my y-axis. And since I have a horizontal asymptote, that means I'm probably up here rather than up here, because otherwise I'd have to cut through, and it could happen. So I could plug in a 4 and see whether I'm up above or below that 1. But I know I'm positive. Then what are we going to test? Well, between 2 and 3. Now here's the cool thing. Do I have any multiplicities? Or are these all to the power of 1 when we factor?
All ones.
What do we say when it's odd? What is it going to do? Go to the what? Odd multiplicity went to the opposite side. Even was the same. It hit that thing and then went back. Okay. So I already know, since these are all odd multiplicities, that guess what all of my signs are going to do? My y values are going to do.
Go to the opposite side.
Which
Negative.
means all I needed was that 1. I know that this is going to be negative, positive, negative. Now, if you don't believe me, we can test any and every one of these, like in between here. What's a good number between -2 and 2?
0.
Plug in 0. Plug in 0 there, there, and there. This would be a negative times a positive, so a negative. On bottom, positive and a negative, so another negative. See how it gives me a positive? Negative divided by negative. And again, we could test something like 2.5. 2.5 minus 3, negative. 2.5 plus 2, positive. 2.5 plus 2, positive again. And 2.5 minus 2, still positive. So you can see that a negative divided by a positive, negative. I don't ever want to test all of them. I'd rather just know my multiplicity trick and just alternate signs when they're odd. But let's say that this one right here was even. It was a 2 or a 4. Then what would we do about this? Positive, negative. What would we put here?
Negative.
Opposite.
Be the same. Right? It'd be the same about that multiplicity of even. So that's the fast way. That's the shortcut that you can do to graph these things. Okay. Otherwise, we're pretty much done. Let's fill in our graph. Let's sketch it. What do we got here? To the right of 3, what do we know all our y values are?
Positive.
Good. So that means above the x-axis. And then between 2 and 3, just right here, we know it's what?
Negative.
And don't forget, we had a few points that we could have plotted, right? Our x-intercept was at 3, 0 and -2, 0. But that one we had to take out because we noticed that it was a hole. And so we had this -2, 5/4, which -2, 5/4 we put right here as our hole. Then the other point we had was 0, 3/2. So that would be right here. And so we know that this is going to be a positive. It's going to have to hit through that and go down here to negative. So everything to the right of 3 was positive. Between 2 and 3 is negative. And between -2 and 2 is what?
Positive.
So here's -2 and here's 2. It's all positive, which means I have to approach my asymptote up here. I have to go through this line, so it's got to have some curvature to it. Hit my y-intercept. I also know it's going to hit this point. Okay, so the multiplicities thing, remember I was telling you, we do have a multiplicity there. They're just on opposite sides, right? We have one here and one there for 2. So that's why this one would actually be the same. And how I figured that out was I just plugged in -infinity out here, or like -100. So that would be a negative there if I put in -100, negative there, negative there, and negative there. So it would actually be a positive there. That was my oversight. Apologies. So yeah, this one would actually be positive, which makes more sense. We'd hit that hole and then come back up, going through that hole, but not crossing to the negative side of our y value. Okay, and again, it's a sketch, pretty ugly, but look at all the things that we were able to do without any type of graphing tool. A lot of this should be familiar. This is the one thing that's a little bit different. And that's just seeing where our y's actually play to all of our zeros. And again, my apologies for that oversight there. Okay. So the nice thing is about this section, 5.7, we've already talked about inverses. All right. Inverses, this should go pretty quickly. Remember we talked about the inverse is just a fancy math term for reverse. Very good. Inputs and outputs. So in this case, we're talking about taking the f of x and writing it as a y because that's easier. So I usually just skip this step, right? But we're just going to reverse or interchange our x's and y's, all of them. And then we're going to solve for that new y. Just don't forget to put that -1 on the y or the f to let me know that it is the inverse. That's the symbol we use. Okay. To verify if inverses are what two functions are of each other, that means they would undo one another. Whether we do f of g or g of f, we would get what we put in that x value, whatever it is. That's what we would get out. Okay, so we've already done this before. The only difference is we're going to be talking about these radical functions now, things with roots or radicals in them, as well as the ones that we just went over, which were rational functions. Okay, so I'll do one. We've already done roots. We've already done all of this. But remember, sometimes we had to restrict the domain. And the reason we restricted the domain was so that the inverse would also be a function. Do you remember how we checked whether or not the inverse was going to be a function? How did we tell if something was a function?
If it had one output only.
And how do we test that if it was a graph? Because that's hard to test algebraically.
Horizontal line test.
Good, close, Jenny. The vertical line test tested whether it was a function to see if its inverse, when we reversed everything, would be a function. We took the vertical line test and we made it horizontal. Very good. Okay. But a lot of times we don't have the graphs already. So again, hopefully you remember this. If it's not that one-to-one, then it can't have an inverse because it wouldn't function, and we only like things that function well. So if we wanted to find the inverse of this, we're just going to first off let this be a y because it's easier. But to find the inverse, we have to reverse what we had. So now it's going to be x equals. Everything else would remain the same. Okay, does everybody see that this and that is the same other than the x's and the y's I reversed?
Yep.
But remember, that's the first step. Second step, solve for the new y. Problem is, there's two of them, and there's a fraction in my equation. But the cool thing is I know what this means, and I know how to get rid of a denominator. I'm just going to take this and multiply by y minus 2. Now, I don't have to do it to top and bottom. I don't need to multiply by a fancy 1 because this is an equation. And if it says that this side is equal to this side, well, then if I multiply both sides by the same thing, it will remain equal. Why did we do that? So that the y minus 2's cancel out and I no longer have a fraction in my equation. But I'm going to go ahead and distribute. So I get an xy minus 2x on one side and then the y plus 3 and a bunch of ones on the other. Now the issue with this is I have a y here and a y there. I need to get those on the same side. So I'm going to do a couple of quick little additions and subtractions. One, let's subtract the 3 over. And then the other, let's move the xy, or do you guys want to go the other way? It doesn't matter. If you want to add the 2x over and subtract the y, that might actually be a little bit easier, huh? Order doesn't matter. That's the cool thing. As long as you do it to both sides, all good. Y's cancel, 2x's cancel. So now I'm just left with an xy minus y on one side and a 2x added to the 3 on the other. Everybody all good there? So I first switched the x's and y's. Second, I got rid of my denominator by multiplying it to both sides, cleaned it up, and then I wanted to get my y's on the same side. Problem is, there's still 2 of them. How do I take these 2 y's and get it narrowed down to 1?
Factor.
Very good. Each of these have a common factor of y. And how do we undo dividing?
Multiply.
So I will undo the dividing by y by multiplying by y so that I can actually do this to just the left side and not have to do it to the other. We're literally multiplying by a 1. We're multiplying by y and dividing by y. We usually just don't write it on the outside. Okay. So now I took my 2 y's and got it down to 1. And remember, that's our goal, was to get that by itself. So the last thing we want to do is undo the multiplying of x minus 1 to get my inverse function, my y. And it makes sense that I had a rational function and its inverse is also a rational function. Everybody good with that? Nothing really new there. Hopefully you feel comfortable with it. That's the nice thing. So the last thing I wanted to make sure that you remember is if I had something squared or cubed, and notice they do have a stipulation on it. So I want you to find the inverse and graph both. So let's start by graphing the original function. Does everybody remember what this looks like?
Parabola.
Very good. It is a parabola. There's my x squared. But what is this doing to that original x squared?
To the left, 3.
Thank you, Beyonce. To the left, to the left. I mean, Mel, thank you. All right. How many?
3.
Negative. That's
Negative.
why she said left, right? Remember, x is always going to be the opposite. So I'm going to take my 1, 2, 3 marches to the left, and I will build my parent function of x squared, which means here I will go over 1, up 1, because I know when I square 1, I get 1, whether I go to the right or to the left. And when I go over 2, I will go up 1, 2, 3, 4, or over to this direction. And before I actually draw this, remember they said that there are some stipulations. What do they only want? X values that are greater than or equal to -3. That means none of this half. Jenny, why? Is this a function?
Because it passes the horizontal line test.
Very good. Of course, this is a function. They told us that at the beginning. It passes the vertical line test. But like Jenny said, it would not have passed the horizontal line test unless they got rid of that other half like they did. Okay, so that's why the stipulation is there, so that we can find the inverse. Right? So I'm going to build this real quick. Over 1, up 1, over 2, up 1, 2, 3, 4, and so on. Now, can I draw the inverses function without even doing and finding the inverse?
And couldn't you technically like reflect it across the x-axis?
Ooh, close. It's not just the x-axis, Jenny. It is across what?
Reflected across both, right?
Yeah. I mean, you could think of it as that. I'm looking for a little bit more.
The vertical axis is what?
It is the line y equals x. Do you guys remember why it's y equals x? What is the inverse of y equals x?
X equals y.
It's the same thing. That's right. So what Mel said was by doing both. Well, what does that mean? Well, remember, what is this point right here?
-3, 0.
What is this point right here, the second one?
-2, 1.
And this one up here?
-1, 5. 4.
And what are we trying to find?
Inverse.
And how do we find the inverse?
Flip it around.
The
And
points.
that means I can take every one of these 3 points and just flip flop them. Take the X and the Y and switch them. And boom, I'd have the inverse graph.
Okay.
But this is my mirror. This is my line of symmetry there. So -3, 0 is going to become 0, -3. -2, 1, 1, -2. -1, 4, or -1. And as you all can see, there's my beautiful butterfly. I didn't even graph or need the function. I can already do the graph of it from the original. But just to show you what we would do to find it, remember, I'll just let this be y because it's easier. And then I will say, all right, well, that's going to be the x, this is going to be the y, and the original function stays the same. Now, what's going to be my first step? Take the square root to undo the squaring. And that now gets that y plus 3 out, and then I'd have the square root of x. Then careful, my last step would actually be to subtract 3. And that would be my inverse function, my y. But it would be the square root of x and then -3. Make sure that you do not force that -3 underneath it. And if you guys remember, the square root of x functions looked like the square root, like this. But it would be shifted down 1, 2, 3, just like we worked on at the beginning of this unit. Square root of 1 is 1, which is why we'd move up 1. Square root of 2, 3, 4 is 2, which is how we get that other point. If we didn't know that we could just flip-flop those ones that we already had. Cool? Quick and easy, nothing too new there really. This is all stuff that we've done, so quick and simple with that one. Last section, 5.9 is gonna combine all that stuff that we just did from not just today or even last week, but from earlier on in this unit when we were solving equations. Because now those polynomials and what we added on today, those fraction or rational functions, they're now going to have inequalities with them. Okay, so you can write down all the steps if you'd like to. That's why I put those on there, just in case anybody wants to pause it and go back and take a look at those, write them down. But you guys already know. What is this asking us to do? And don't just say solve. I can read. What does that mean? What do they want us to find?
Our x's.
I know it's a tough task. You don't always want to do it. But yeah, we got to find our x's. And not just the x's. We want to find our what x's? Ones that are less than 0, meaning they're what?
Negative.
Yeah, the negative x's. We got to go there, guys. Now, keep in mind, you can plug in numbers into this polynomial that are positive that will make it negative. So your answers won't always be negative, but you need to know that this right here means we want negative answers. Now, if I wanted to, I could have said, you know what? Don't even worry about this. This is my function. Do you guys see that? And this is our quadratic functions, those parabolas. That's virtually what we're dealing with here. But what do we always like these equations to be equal to? Beautiful. The only problem is we like them to be equal to 0, not less than, not greater than, or less than or equal to, or greater than or equal to. We like them equal to 0 because we know how to solve that, don't we? Forget it then. Let's just do that. Let's just forget about the equal to right now, or the less than, and just make it an equal to, because we can do that, can't we? What's our quickest, easiest method to solving this? Polynomial. Quadratic polynomial.
Factor.
If we can, very good. And if we can't factor, Mel, what did you say?
I also said factoring.
Good. What else could we do?
Quadratic formula.
Good. Because it's a quadratic, we can use quadratic formula, or if we can't factor and the quadratic formula is a little bit long, what was the third?
Completing the square?
Yes. You dug deep for that one. Very good, Jenny. Completing the square. We have that option as well. Your choice. What's the quickest, easiest method? Factoring. That's why we learned how to do it first. Some of you still haven't learned how to do completing the square, which is why you don't even remember it. Okay. So with this, we hope that it is factorable. X and X, when I FOIL distribute, will give me the X squared. Then I look at the other end, -8. First thing that comes to mind, 4 and 2. And that does combine to this. I just got to make sure that my signs work out for this and that, here and here, and it's factorable. +4 and -2 to combine to my +2 and multiply to -8. Beautiful. Then that tells me right then and there that I just found two, what are we going to call these?
Roots, x's.
Zeros. Yep. We can call them X-intercepts, solution, whatever you want. I know at what and what X value would make this equal to 0.
-4 and 2.
We've been doing that so much we don't even have to think about it. We just take the opposite. We know that would get us back to 0. That's not what they wanted, you guys. Don't be boxing that in. That is not our answer yet. That's where it would equal 0. But if that was f of x equals x squared plus 2x minus 8, we just found when f of x, my y value, would be equal to 0. What do they want to know? Where our y values are what?
Less than 0.
Which is just like we talked about 15 minutes ago. If I just take those two things, -4 and 2, and I think about those as my X-intercepts, as Jenny mentioned, where this whole thing would be equal to 0, then can't we find where this thing would be less than 0? What would that mean it would come out if it's less than 0?
Negative.
So all I'm going to do is I'm going to go over to this, and I know that because there were 2 places where it was 0, then there are 3 different regions, sections, or what they call intervals, that either have to be what or what?
Negative or positive.
Because these are where it's equal to 0, only those 2 places. So if it's not 0, it either is positive or negative. Done deal. And since both of these are a multiplicity of what?
1.
There's only one of these and one of these because it's not rational or fractional. Then I know whatever I find out here or out here that I'm just going to alternate. So I always like to start off positive. I'm going to test 100. I just always choose 100 because that's what I like to keep it in here. Should have used red, huh? Okay. For all my emoji fans out there, if I'm plugging in 100, I'm going to do it here and here. I'm not going to go back to my original. That's nasty. Because all I care is that if it comes out what or what.
Positive or negative?
I don't care what value it actually gives me. I'm not trying to graph this. I just want all the things that are less than 0. So plug in 100 here and here and tell me, what do we get, positive or negative?
Positive.
Beautiful. Then I know a positive times a positive is going to stay positive. And do I have to check something between here like 0 and out here like negative 100?
No, it alternates.
Yeah, I can, but because I know those multiplicities about my zeros, like Jenny said, I'm going to know that this is going to have to be negative and that's going to have to be positive, which, careful, means that since they put strictly less than 0, what am I going to put for my solution set?
The domain of -4 to 2.
Good. I didn't want any of the positives out here. Let me use a different color. I didn't want the positives. I only wanted the things that were strictly less than 0, not even the things that were equal to 0. So Brian, what should I be putting? From left to right, when do I start hitting my solution set?
Bracket of -4.
-4, you said bracket?
Well, wait, parentheses.
Ah, good. Because if I stuck in -4 here and worked it out, what do I know I would get?
0.
And did that make this true?
Nope.
Then it is not a solution. But -3.9999999 for all you inglorious people out there, for my movie buffs, works. And I don't want to leave any answers out, so I'm going to say, you know what? Not -4, but from there all the way to 2, not including 2. All of this stuff. Now, how could I have changed those to brackets, Brian?
Less than or equal to. Yeah.
Put an equal to sign. Now we have to include those zeros. Very good. Excellent. That, again, my friends, is called interval notation. And what I want you to be very careful about when you're doing this group quiz and the exam next week, pay attention to those parentheses and those brackets. They matter. Okay? So there's our example of a polynomial. Let's do one for rational. And then that's it. That's all I got. Okay, so this last one here, again, they're going to give you the how to, all these 5 steps. You guys know what you need to do. I don't like the look of this. I need to get it set equal to 0. And do we like fractions all split up like this? No, thank you. We want to get one thing over another set equal to 0. And once we find our zeros, then we can test what they call the critical points, however many there are. And then once we do that, we'll find whether they're positive, negative, positive, or any that stay the same due to the multiplicities. Not a whole lot different. Okay, I'm going to start by subtracting the 1 over x. So now on the left side, I have 1/2 minus 1 over x minus 3 over 2x squared, all greater than or equal to. That canceled out to be a 0. Now, of course, in order to do any of the adding or subtracting with fractions, we need a common denominator. And the only way that we can get that, remember, is, of course, now you might be seeing that I actually do speak some truths. We got to multiply by that fancy 1 yet again. So this case, x squared over x squared will get it done. This one here would be a 2x over 2x. And this one is all good. So I got an x squared over 2x squared minus a 2x over 2x squared minus a 3 over 2x squared. All greater than or equal to 0. That now allows me to finally have x squared minus 2x minus 3 over a 2x squared. And now I got my one fraction with my sign. Now remember, the only thing you got to be careful with inequalities is if you multiply or divide by a negative. Remember, if you multiply or divide by a negative, that's going to have the opposite effect. Everything will change to the opposite sign, which means you also have to switch this to the opposite. So if you want to make a note of that, okay, if you ever multiply or divide by a negative, must flip. Your sign, your inequality. Okay, hopefully we don't run into that, but I wanted to make a note of it. So what do we got? Well, just like before, I want this and this. I want to know when they equal 0. I'll deal with this later. Okay, the bottom one's super easy. Set that equal to 0. Divide by 2, that's gone. Take the square root, we just get one answer, it's 0. But technically, it's how many zeros? Two. Okay, so the last thing we're going to do is we're going to set this top, which I'm going to go ahead and factor, and this bottom, which already is factored, and we're going to set each equal to 0. So on the top, I get an x or 0 of 3 and negative 1. On the bottom, I get an x of 0, but with the multiplicity of 2. Do you guys see that? That's going to come into play because now we will go ahead and draw out our number line for our x's, which is at, we said, careful, not the order that you found them in, but left to right, smallest to biggest number line, -1, 0, and 3. And I like to just extend it out so that you can see with 3 zeros, we have 1, 2, 3, 4 different regions. And I know out here, I'm going to test 100. And I don't really have to test anything down here. Because what happens when we square anything? What does it always come out?
Positive.
Times a positive 2. Everything's going to be positive, so we're really just focusing on the top. And why do I choose 100? Really easy. Everything comes out positive when you subtract 3 or add 1. So what usually happens out there is you get positive. So be careful. What is the next interval going to be without actually going through and doing all that?
Negative.
Good. What's the next one going to be?
Positive.
Are you, Jenny? Because you don't sound like it.
Isn't it because it has a multiplicity?
Oh, good. But you didn't do it correctly. You saw it, but what does it mean if it has a multiplicity that is even?
It's the same, it goes through.
So since we know it's negative over here, what is it going to be over here?
Negative.
The same. Very good. And then what is it at -1? The multiplicity of 1. So it's odd, which means it's going to be the opposite. And do you see how we can test that very quickly without actually having to do it for each and every one? Just by knowing the multiplicities that we went over earlier in this chapter. Okay, so all of this is finding my what values? Well, what are these?
Your x's.
Good. So what are all of these representing?
The y's.
Good. If we were to graph it, we could use this or not. They're asking us for all the things that were what?
Greater than 0.
Okay, not just greater than 0 this time, Jenny. It's like Brian mentioned last time.
Or equal to.
Good. Now that matters, and I got to make sure that I make a note of this for you all. But we definitely know we're going to toss out all of the negative things. We're just going to keep the positive ones for sure, because that's the greater than 0 part. But don't leave out the equal to. Are all of these going to be solid dots included? Are they all going to give me zeros? In my original function here that we ended up using, what should you never include a 0 of?
Denominator.
Very good. Why not the denominator? Even though this is equal to 0, can we take any number and divide by it? Is that going to give us a 0?
Mm,
No, like Mel said earlier, it's only the top, the numerator, that would actually equal 0. So my suggestion to you is put the not equal to 0 on bottom to remind yourselves. So the 0, I always, when I graph, will put an open dot, and the numerators, I will put the closed dots. So I don't have to go back and think about it. I have them there. Then I'll get all of these, and then I'm done. Okay? So how do we write our final answer for that one? We wanted all the things that were greater than or equal to 0. That were these and not the negatives. And remember, we like to read it from smallest to biggest, so from left to right. Where are we starting?
Parentheses, negative infinity to -1 with a bracket.
Oh, good. Very good, Brian. He learned his lesson all the way out here. This one is included. This one was in the denominator, so not, and none of this. So we would jump all the way from here to, we got to unite. Is 3 included in this?
Yes.
Bracket all the way to positive infinity. And remember, infinities are not included because we cannot physically plug those in.